My name is Aza, and I'm a senior researcher and data scientist at Ghent University, and I'm visiting postdoc at Princeton University. Having the honor to work with Egemen. Well, the talk today is about real-time remote sensing and fusion plasma control, and as Egemen said, I'm trying to use reservoir computing to solve the problems, trying to solve the problems. But first of all, what do we expect from this talk? Well, I wrote it in like a pseudocode thingy. It depends on what you know. So if Kx is your knowledge about X, then we have this. Well, if you're new to machine learning, then I hope I give you some ideas on like how to better explore the ML area, how to better choose which model you should use for your data, depending on the task and depending on the difficulties and all the limitations that you have. Well, if you are familiar with machine learning, but you haven't heard about reservoir computing networks, I hope by the end of this presentation, you are convinced at least to consider some alternative machine learning techniques as opposed to like the mainstream models like deep neural network and convolutional neural networks. Well, if you know about machine learning and also know reservoir computing, but you haven't heard about the application of reservoir computing for fusion data, well, this is a new use case. I hope you enjoy it. If you know machine learning, you know reservoir computing, you have already applied that for fusion data, well, then probably you are me. So then I would be happy. So please continue this talk for me. And if you're none of the above, just go and take a bucket of popcorn, sit back and enjoy the presentation, hopefully. Anyhow, let's begin with a true story. A few days ago, I thought, okay, so I have these 8 toy apples, green and red-ish. I put it in my hand, and is it possible to somehow put a straight line to separate greens from reds? What would be the accuracy of that straight line to separate these two environments, these two objects? If you do your best, I think this is the best line, the best straight line that you can come up with. Saying that, okay, this is the line, the right side belongs to green, red, left belongs to red. So that gives you 2 errors, like this red apple is in the green area, this green apple is in the red area. This one, okay, let's consider that in the red area, so that's correct. That gives you like 75% accuracy. How can we improve it? Well, there are many ways. This is what I tried. Voila. So it was very simple. I just left them and they hit the ground, and for some magics, they are separated from each other in this, well, flat but bigger surface, and now I can easily separate them with 100% accuracy. But how did it happen? So let's look at it again. So far we cannot still put a straight line to separate them perfectly. But now it goes down, so it is still impossible to do that. This is a turning point. Like if you look at this little green apple, for some magics, for some nonlinearity or dynamics or whatever, it starts to fly to the right side, and hopefully, well, I was lucky that none of the red ones went to the right and the other way around. So I was lucky that they stayed in the correct place. Now I can separate them very nicely with 100% accuracy. We will come back to that later. That's just to give you like an idea about how this random process helps to improve the accuracy of separating these 2 classes. But now a real problem. Well, we all know about climate change. I'm not going to repeat all these sad stories. Well, our planet is green with blue sky, but because of the abusing of the resources, the fossil fuel, the climate change is happening. And if we are not careful, after some time, we will end up with this disaster, and we don't want that, right? So we want to look back to the sustainable, nice, green environment, not only for us, but for all the other species. So we need to replace fossil fuel with something more sustainable, green, renewable energy. There are many options like solar panels, wind turbine, and one of the most promising alternatives is actually fusion-based reactors. And this is in the context of a big project which is called ITER, and ITER has the headquarters in France, but well, it's a multinational project, so many countries are involved. And how does it work? So we have like a reactor. It has like a donut-shaped space in which we have this magnetic confinement in this donut shape, which holds all these particles like this deuterium and tritium together. And if we heat it up high enough, I mean in the order of 150 million degrees, it forces these atoms to fuse together, and this fusion makes energy. And if we are lucky enough that this produced energy is higher than the energy that we spend to heat up the whole environment, then we have some extra energy that can be used for other purposes. So that's the whole idea of fusion-based reactors, which is also called tokamak. But so we are talking about a plasma environment. We are talking about like very high degree of temperature, and everything has to come together to make this happen. So we should have enough density of particles for a long time with high enough temperature for this fusion to be effective. So of course we are working on the edge, and any kind of instabilities might lead to like a problem. Let's say, well, the problem will not be something like Chernobyl, but it damages the device. So it is very crucial to avoid these instabilities. But like many other complex physics phenomena, there are not only like 2 or 3 or 4 parameters to control. Otherwise, it could have been very easy to control it with physics-based models. But now we are talking about, I don't know, hundreds or thousands of parameters. Some of them are even unknown for physicists, let alone for controlling them. So now this is the problem. We have a lot of parameters, known, unknown. We don't have a reliable physics-based model to control this plasma, to control these instabilities, but we still want to have this tokamak to work. What should we do? Well, although we don't have this physics-based model, but we have the data. So why don't we let artificial intelligence and data science come into play and solve the problem for us and find the pattern within these data that we have collected? This is actually the hero data scientists come into play. And that's my story. So again, just to formulate the problem, we want to detect, predict, and prevent plasma instabilities. There are challenges, many known and unknown parameters. Even interpreting plasma behavior, sometimes it's difficult for physicists to do that. And well, we want to have a lot of data about instabilities, but all these instabilities make damage to the device. So although we have these experimental tokamaks these days, like in San Diego, in the UK, in MIT, in the US, well, and in the other countries. But it is very expensive to push them towards these instabilities and then try to collect the data. So we have lack of data. And these are all about experimental machines. What if ITER machine becomes functional, hopefully within like 20, 25 years? Such a big machine doesn't give any room for error. So we are not going to test and to try and error our models in that ITER machine. So whatever we do, we should do it in the small machines, and it should be adaptable and transferable to the big one. And like in the right side, you see like a few of these parameters, like electron density, ion rotation, electron temperature, and rotational transport and plasma pressure. These are some of the most important parameters that have to be controlled and predicted to be able to control the plasma behavior. So now the question is, can we actually predict these profiles, these 5 particular profiles of plasma, by only looking at the time t and these profiles and predict it in like next 200, 300, 100 milliseconds? And as you see, it is actually like high dimensional data. So here we have time, and each of these profiles have like 65 probes. So we are talking about 5 times 65 probes only for these 5 parameters. We also have some actuators which are controlled by the engineers, and there are many more parameters that we don't take into account in this particular presentation. So the problem, we want to move from fusion data to machine learning, and this is where the second story comes into play. From fusion to machine learning. Let's take a look at an example. Assuming that you are new to a city like Paris, or you are a tourist in Paris and you want to do awesome things. Well, if you are new and that's the first time in Paris, where would you go? Well, there are many options, but I assume many of you would like to go to Eiffel Tower. Of course, why not? That's one of a kind. Okay, so you go to Paris, you go to Eiffel. What to do? Of course, well, buy souvenirs, take some pictures, nice pictures. That's actually the picture that I took. And okay, you have been there, and now you want to share your experience with your friends and family, maybe to show up, maybe to make them happy, or maybe just to say that, well, I've been there. What do? Well, you share it on social media, you get a lot of likes, reactions, and mission complete. You have proven that you have been in Paris and you did something awesome. That's more or less the same thing that happens for those who are new in machine learning and want to do something awesome. What's the most awesome thing in machine learning these days? Convolutional neural network, deep learning. So, okay, I'm new to machine learning. I have some data. How can I model it? Google it. You do some literature study and Google. Well, deep learning seems to be awesome. Let's try that. But what to do? I don't know how to configure this model. I don't know what the parameters are. I don't know how to optimize it. There are a lot of pre-trained models like this ResNet and the others. Well, let's try them. So you say that, yeah, I take this ResNet and, well, I want to do some classification. What kind of classification? Then you see, yeah, well, I have this, let's say, bottle or mug, and I have phone. These are in my hands. Let's try to have this mug phone classifier with ResNet. That's quite easy. So you have this pre-trained model. You just drop the last layer of ResNet and train it for these 2 classes. And well, if you have enough data, if you have enough diverse data, it would probably work. Very good. You have your first deep learning model to classify mug and phone. It's a success. Now, what you want to do? Well, you want to share it. How? Well, let's publish a paper. So you write a paper with fancy topic, fancy title and authors. And if you are lucky enough, well, you get a very easygoing reviewers, and your paper is published. The same as being new in Paris, mission complete. Well, you have a paper in deep learning in no time. But you know, if you really want to feel the soul of Paris, you should go to these hidden corners, or like these cafes in the back street. This is where you see like real Paris. That's the same here in machine learning. If you really want to do machine learning, if you really want to learn how it works and how to use it for your data, you should dig into that. You should go to you should know all these alternatives that could work even better than deep learning, depending on the task that you have. And this is actually the main part of my presentation today, to give you a hint about one of these hidden corners in machine learning, which is called reservoir computing networks. For those of you who are not very much familiar with neural networks, I just give like a brief introduction from simple multi-layer perceptron to reservoir computing. Well, multi-layer perceptron consists of an input layer, some hidden layers, and an output layer that actually tries to classify or do the task for you. These hidden layers are structured in like in separate layers, and the input of each layer is actually the output of the previous layer. So each layer tries to give like a richer representation of the input and give it to the next layer, so on and so forth, with the hope that the last hidden layer provides rich enough feature which make the classification or the task much easier. So we have this internal representation of the input. But well, one of the problems with multi-layer perceptron is that it doesn't have any memory. So at each time step, it only looks at that time and it doesn't know what has happened in the past. It doesn't have any memory. And of course, if you want to do temporal information processing, like time series data, it would be very handy if the model has some sort of memory, because we are not only interested in what's happening right now, but we want to make a pattern from the past. And this is where recurrent neural networks come into play. So recurrent neural networks are actually those MLPs, but there are also some recurrent connections among the nodes in the hidden layers. And well, now you can see what's going to happen. So like, let's say this node not only sees the input from the previous layer at time t, but it also sees the output of the next layer from t-1. So that information from t-1 is some sort of memory that is provided to this node. So now this node has some idea about what has happened in the past, and that makes some sort of memory. And that makes recurrent neural networks very good for temporal information processing. Very good. But the bad news is training of recurrent neural network is way more difficult than MLPs because of this backpropagation problem. What does it mean? It means that, well, if you want to, let's say, if you update this weight from right to left, that will affect this node. And then that means it affects this weight, and then it affects this weight, and then so on and so forth. So you see there is some kind of loop of updating the weights. And the error that has been, that has been provided, that has been calculated to rectify the model, somehow gets lost in this soup of weights. And that's what makes training of recurrent neural networks very difficult. And this is where reservoir computing comes into play. Reservoir computing in general is very similar to recurrent neural network with two big differences. First of all, we don't have these structured hidden layers. We just have like a pool of nodes, a pool of hidden nodes, which are actually randomly connected to each other and also connected to the input layer. So all these blue weights that you see here are initialized randomly, and they are not trained at all, and they will not be trained. So they are just initialized randomly, and the only weights which are trained are the red ones, from the hidden nodes to the output, using only linear regression. Assuming that it works, it solves some problems. First of all, because of these recurrent connections, this model still has some sort of memory, so it is good for temporal information processing. But not like recurrent neural network, we don't have backpropagation here because we are not going to train these recurrent weights. We only train the output weights, so we don't have backpropagation. That's great. So we have a model with memory, but with much easier training process. But of course, well, nothing comes for free. One of the disadvantages could be that, well, if you can solve a problem with 50 hidden nodes in recurrent neural network, you might need like 200 nodes in reservoir computing to solve the same problem and get the same performance. But that's the cost that you pay. On the other hand, developing these models is much easier than recurrent neural network. So who cares about like having a little bit larger model? To give you an idea about the efficiency of these randomized neural networks, I think this plot could help. Well, this is actually a quote from Haskell paper that says randomization is computationally cheaper than optimization, but it's still getting the same comparable performance to the optimized model. So that means, well, it would make sense to try a lot of random models, like bigger random models, rather than optimizing a small model. If we look at this plot, it says that, well, linear models are, well, very low complexity, we know that, but they also have low accuracy. On the other side of the spectrum, we have deep convolutional neural network, which are very, very complex models, but of course with very high accuracy. Models like support vector machines stay somewhere in the middle. But you know that it has been shown that these deep randomized neural networks have much lower complexity compared to deep convolutional neural network. But as you see, the difference in the accuracy is not that high. So that makes them very interesting for complex problems where you need nonlinearity, where you need memory. But actually, how does it work? I mean, how on earth these randomly initialized model work? Here I try to somehow give you like a simple example that I hope helps you to understand what's happening here. Let's say that we have these 10 objects, circles and triangles, and we want to separate them using a line. The best line that you can come up with is this one, and saying that the right side belongs to triangles and left side belongs to circles. That gives you 4 errors. Two circles here and 2 triangles on the left, they are misclassified. So we scored 6 out of them. Now we have this 1D dimension input, and we use a reservoir with 2 nodes. So since we have 2 nodes and 1 dimension input, the input layer has these 2 elements. So from 1D to 2D to connect this 1D dimension to these 2 nodes. And these 2 nodes are connected to each other in 4 directions, like each node to itself, and node A to B and node B to A. So we have 4 weights here for the recurrent connections and 2 weights for the input connection. And these are actually those weights that I showed you in blue, which are initialized randomly. And then we apply this nonlinear function like hyperbolic tangent or whatever nonlinear function that you like. If you apply this particular model with these weights to this input feature space, we will get something like this. And voila, now you have better classification. Why? Because this reservoir helped you to map this 1D input feature into a larger, here, 2D random but nonlinear feature space. And that improved the accuracy of linear regression. Isn't it a bit familiar? Isn't it similar to what I showed you at the beginning? Well, they are more or less the same concept. In the first one, I showed you classification of these apples, and their randomization and this nonlinearity were all based on the physics law of like gravity and well, this shape of the apples that help when they hit the ground, they might fly any direction. Well, not any direction. If you know all the parameters there, like the, I don't know, the weather, the temperature, the humidity, or whatever the material that these apples have been made of, well, you can precisely predict where these apples go, but well, it's just too complex, you can say it's random. So you see, these are the same concept. If you believe that the apple problem is valid, you can also imagine that reservoir computing works as well. Okay, so let's go back to our fusion problem. So we had these 5 profiles, and we wanted to predict these profiles 200 milliseconds later with the help of some actuators. So at each time step, the model, the machine learning model, which has been shown with F here, receives the profile values at time t plus these actuators and predicts what has happened, what's going to happen in 200 milliseconds. That's the definition of the problem. And this is the data that we have. Every time we run this tokamak for, let's say, for one run, it's called a shot. For this particular problem, we collected all the shots from the year 2013 to 2018. So we collected all these shots, the parameters of all these shots. And we came up with this data set, the big data set that we had. Then we thought, okay, so let's try the famous ConvNet and LSTM on that. First of all, training a ConvNet and LSTM on this data set took like 5 hours on high performance computers on GPUs. Like it took like 5 hours. And in the plot below, you see the error measure when we applied this trained model on the same data set and the same campaign of 2013 to 2018. Well, let's assume that it is very good prediction. So the error measure is actually very low. How do we know that? Because then we thought, okay, so the model has been trained on the campaign of 2013 to 2018. Why don't we try it on the data set of 2019 and see how it works? And this is where the disaster happens. So the error measure almost doubles when we tried that pre-trained model on the new data set, probably because the configuration of the tokamak changed in 2019, or maybe the physicists, the experts, I don't know, ran some new experiments with very new setups. So what we have seen here is that ConvNet, this deep neural network, performed very well on the data set that it has been trained with, but it didn't work well when the data changed. And then we thought, okay, let's try reservoir computing. First of all, training a reservoir computing of, I believe, like 500 nodes took only 45 seconds, and not on HPC, on a single CPU on this typical i7 CPU on a desktop computer. So it took only 45 seconds. And how did it work? First of all, well, I mean, the first look says that, well, RCN is very similar to CNN. It performs a little bit worse in the scene data set, and it performs a little bit better on the new data set, which has not been seen before. Well, it is okay, but it's a bit disappointing, right? I'm talking about like for half an hour about how great reservoir computing is, and now we see that, okay, it performs similar to CNN. So what's the point of using that? First, there are actually 2 points here. First of all, as I said, it took only 45 seconds on CPU compared to 5 hours training on GPU. And you know, this seminar is being held in the Center of Energy and Environment, so we care about these things, right? So why should we waste a lot of energy, like 5 hours of energy of this HPC, when we can do the same thing with only 45 seconds of CPU? So that's one reason. The second reason, we will see it a bit later. But first of all, let's take a look at one example, how Reservoir predicted one of these shots for one of these parameters. So this shows the electron density of one of the shots. X-axis is time, and the dashed line is actually the truth, the real profile measure. And the blue line is what Reservoir has predicted. At the beginning, it's a bit off, then it gets better until this moment of, let's say, change. When the truth goes down, Reservoir goes down as well, but it goes too down, let's say, and it stays there. It doesn't know that it has to rectify itself. And this is where actually the main error happens. So this is the performance of the Reservoir that has been trained on 2013, 2018, and has been tested on 2019. Well, it's bad, it's disappointing, but the good news is we can actually adapt this model which is almost impossible or very difficult for CNN LSTM. Why is that? Because, as I said, training of reservoir computing is way faster and easier than gradient descent and piece backpropagation, these things that we use for convolutional neural network. Basically, we showed that we can retrain and adapt the reservoir computing every 100 milliseconds. It's so fast that we can actually adapt the model when the shot is running, because the shot runs for, let's say, 5 seconds. So we can do it several times, like 50 times within each run. And I won't go into details of this adaptation. If you have a specific question, we can discuss about it later. But we actually try to adapt the model every 500 milliseconds. So that means the model first trained on the previous data, 2013, 2018. But whenever we have a new shot, every 500 milliseconds we collect that data and adapt the reservoir computing. Again, 500 milliseconds, adapt, and so on and so forth. And see what happens. Very good. So it seems that we solved the problem, because, well, if you look at this performance, first of all, the adapted model improved the error rate very well, and it didn't change much for the scene data set. That means the model is quite robust. And if you look at this particular example, it shows how it rectifies itself. First of all, it follows the same trend of normal RCN up until here. And this is the moment of turn, when after this 500 milliseconds, it learns that it's going wrong, and it rectified itself and follows the correct line quite well. And this is actually the whole idea of adaptation of the model. Of course, well, you can try it on any other problem, depending on the task, depending on the complexity of the model that you need. And this work actually was recently published in one of the highest impact factor journals in the community of data science and machine learning. Well, to conclude, what we have seen here is that there are reservoir computing networks have like very interesting properties. First of all, they are very easy and fast to train. They are suitable for time series data analysis because they have memory. And I didn't go into detail, but if you remember those input and recurrent weights, we have shown that these weights could be actually very, very sparse. Only, let's say, 1% connection would be enough to achieve promising performance. And that makes the whole model very light, very sparse, so that it can easily be implemented on hardware devices. And I just showed you that it's highly adaptive. Depending on the complexity of the model, you might be able to even adapt the model while it is running. And well, of course, there are, well, what I showed in the beginning was actually a one-layer reservoir computing. You can have like multi-layer, so-called deep reservoir computing. You can actually configure the hidden nodes to connect to each other in a specific way to provide some, let's say, specific patterns that might be more suitable for your data set, depending on the task. And it's not only that I showed it worked in plasma condition monitoring, but during my research, I have used reservoir computing for many different types of data. For instance, for speech communication. This is actually the topic of my thesis. So the idea was to use reservoir computing to enhance the speech features, acoustic features, and also to use reservoir for recognizing what has been spoken. And this is actually one of the examples. Maybe I can, okay. No, I think it doesn't work. Anyhow, so this is an example. This is this 1D speech signal. We extracted the acoustic features from there. As you see, it is very noisy. And then we applied reservoir computing to enhance it and to remove the noise. How does it work? So we have this, during the training, we should have this noisy sample and its clean version. And when we train the reservoir, it tries to learn the noise pattern and try to remove it. And then we use that enhanced features for detecting, for recognizing what has been spoken. Another very cool project that I have been involved was to use reservoir computing to identify persons based on their gaits, based on their walking style. So using radar. What's the point of that? Well, it would be interesting for the for the security at home to know who is there, who is not there, who is entering the home, the house. But it's a bit, let's say, intrusive to use normal cameras there. Why? Because well, people don't want to be captured all the time. So that's why we thought, would it be possible to use radar data, which you see on the right side, to identify people? And this radar captures the speed and distance of the moving objects. So the model is supposed to recognize people based on their walking style, because when they move their hands and legs, they provide some sort of unique patterns per person. And well, we showed that it worked. So not only reservoir computing, we also use deep neural network, and we showed that the performances of these two models are quite comparable. Well, this all tells you that, I hope that it tells you that whenever you want to use machine learning techniques for your problem, maybe it's better, it's more effective if instead of jumping to like the mainstream deep neural network, convolutional neural network models, try to explore more the, let's say, more appropriate functions, more appropriate techniques in machine learning that could be, let's say, as useful or even more effective than these complex models. Let's say if you don't have enough data for image processing, you have two options. Either use this pre-trained ResNet and try to adjust it a little bit for your model, or if you want to train this whole complex model from scratch, you need a lot of data. But maybe you can try other models. I don't say reservoir computing, but there are many other options. It's just to give you to convince you that sometimes it's worth to do some more exploration in the area of machine learning and cleverly find the appropriate techniques for you. And well, to wrap up, if you are interested to know more about our research, as you know, I'm affiliated to Ghent University, and also I'm visiting postdoc at Princeton University right now. So if you are interested to know more about the nuclear fusion activities and research in these two groups that I'm involved in, you have these addresses here. I'm sure you will find a lot of interesting stuff there. If you're in particular interested in reservoir computing, you can always contact me. I'd be happy to have a chat of coffee remotely. And well, that's it. Thank you for your time. And I would be happy to answer some questions if I can. Thank you.
Hello. Well, Azza, thank you very much. That was a really nice presentation. Even though I know your work, you put it in a really good format for people who are not familiar with what we're doing and what you're doing. So if you have any questions, you can write it in Q&A or try to write it in. If you can't figure that out, you can put it on the chat box as well. While we're waiting for I have a few questions. The first one is, so if you go back to the adaptive part, so here, so the adaptive part, you're using the previously trained neural net reservoir, and then you're updating the final connection stage. But that adaptation is a linear optimization, right? That's just a linear.
Yes.
So you can think of that as a function that you can build a neural net to basically do a reasonable job of guessing or predicting what that function would be. Do you see what I mean? So can you put an adaptive neural net sort of structure that works with all these type of reservoirs, or can you do something like that kind of generically works for everything, so you don't have to design a different neural net or have an outside function, can you embed the adaptation into the neural net in a way? Does that make
yeah, that makes sense. I think what you mean is some sort of feedback loop that gets the output of the model as the input in the next time and tries to rectify the model based on this feedback loop. And that's actually true. And well, honestly, with one of my students, we are working on that to have like this adaptive reservoir, which gets the output of the model as the feedback, not to all the nodes, but to some of them. And that is used to so the model not only learns the new stuff, but also tries to rectify itself at every sample. So yes, that's actually a very good thing. You can try that.
Charlie has a question.
Hey there. Thanks for that great talk, Azza. So this is all new to me. I was wondering about you showed a slide where you had the projection of the one-dimensional data with the circles and the triangles onto a two-dimensional space. Yeah, that one. And I had two questions related to this. One is, it looks like from the number of, from my view, it looks like maybe the number of triangles is multiplying, but maybe I'm misunderstanding that the same triangle is showing up twice in the new dimension that's been introduced, to give it, just to have a place that it shows up that you can now separate it from the circles. And so one question is, to what determines the extent of the new dimension over which you're projecting the data? How do you figure out what that? I mean, I assume that you can do that by looking at different projection scales or dimensions and then scoring them, but it doesn't seem like that would be an efficient approach to the process. And then my other question is, I'm trying to make the connection between this way of thinking about the process and say the electron density data that was being shown, and trying to draw an analogy between maybe the one dimension is the time, or how does this relate to the physical data that's measured in the fusion experiment?
Yeah, I see. Well, to answer to your first question, well, we have this random model, and we have this input feature space. We want to project it to probably, or let's say, most likely higher feature space, but we don't know how much higher it should be. So it could be like 2 times, it could be just x plus 1. We don't know that. So that is actually one of the hyperparameters that have to be optimized, and that is actually the size of the reservoir. Gotcha. We have shown that, and well, maybe I'm just checking if I have the plot for that. Oh yeah, okay, I have it. That's actually one of the examples. So that's on the data set that I showed for like profile prediction, and in which we try to increase the size of the reservoir from 50 to 8,000. And here you see the performance, the error rate as a function of the reservoir size for training set and validation. So what it tells you is that if you want to optimize the reservoir size, at least in this data set, something like, I don't know, the order of 1,000, between 500 to 1,000 seems to be good enough. So it is actually one of the hyperparameters that I would say by just sweeping and increasing the size, you will find out which is the best region. And also it depends on the complexity of the model that you want to have. And to answer to your second question, the dimension that I'm talking about is the number of the features that we have. Like in that particular data set, we had 5 profiles, and each profile had like 65 elements. That means 5 times 65, 325 input feature. That's the input feature space. And by this plot, it tells you that if we increase the size from 325 to 1,000, the performance is optimized. So by feature space, I mean the number of features that you feed into the model.
Yeah, that makes sense.
Yeah.
Thank you.
So there is a Q&A. There's something. Oh, Garrett is a question. With disruptions being such a, can we allow Garrett to be able to ask it himself, or if not, I'll read it for him. Oh, okay, Garrett. Okay, do you want to ask the question yourself, Garrett? Hey, how are you?
Can
I
you
was
hear
just
me?
writing you a response. Yeah, we can hear you. Go ahead.
Yes, thank you. A great talk. Thank you very much. Well, yeah, that's my question. So disruptions is such a big problem for fusion. So ITER or demo can hardly sustain any disruption at full power. This seems like RCN seems to be able to solve, to go to that holy grail, to reach that holy grail of disruption prediction and being able to generalize from one training set very quickly, to adapt very quickly to a new environment, new machine, new operational scenarios and all that. Don't you think there's a huge potential to disruption prediction for reservoir computing?
Well, from the data science point of view, I can say what I showed you, that it is possible to very quickly adapt the model to this new situation. But there are two things here. One is that at least in this particular data set, as I showed, we could use a reservoir of 500 nodes and it was efficient enough. And that was one of the parameters that make the adaptability very easy. If we had to use a reservoir of, I don't know, 50,000 nodes to make it efficient, then the adaptation also takes longer. So what I'm saying is that it all depends on the complexity of the task and the diversity of the data set that is available for us. So if for disruption prediction, we have like very effective set of input features that can be used to have like a very small, that can be used to train a very small model. Yes, we can do that for adapting the model to the new situation as well. But well, this presentation shows you the potential of the model, but it doesn't tell you that it can solve all the problems.
Right.
Yeah. But there's definitely a potential room for exploration there.
Okay, thank you, and great to see you, Egemen.
Yeah, great seeing you, Garrett.
Yeah.
Well, if you can stick around, Garrett, my main question, this is more not on the research, but on the collaboration side. So I was trying to say this, it kind of was hard. Well, cicadas are jumping on me. I'm outside here. Azza is one of the first people that, he came to our group without seeing anyone. We haven't met in person. No one met in person. And I wanted to ask what he thinks about remote working and collaboration with no initial interaction. So what people have been told, I mean, this is the same for me, I believe, is if you know the place, let's say you're in Princeton University all your life, then you're off site for a year because of COVID. That's kind of okay because you already have the social contacts to be able to continue your work. But you were one of the few people who came without knowing anyone, without having met anyone. How did you make it work? Because you were able to make it work. And what advice you can give to people? I mean, hopefully we won't have to do this again, but who knows? And we might have to do it halfway. What advice can you give people? Because I think you're a really successful example of someone who came in totally remote and took part and lead the research. I didn't say this, but there's students that are working for you over here and in Belgium and so forth. So you're able to connect to the team really well. So can you give some advice on that?
Yeah, thank you for the nice words. But yeah, I think it is quite mutual. First of all, well, people say that I'm very social. I used to organize like events in my office with our people. So I'm used to this kind of to communicate with people. That's from my side. But the other side is also as important. Like the first time that I met your team in the meetings, well, I quickly got connected to them. So like back then, when I was working, when I started to do the research, I think I had the first meetings right after our group meeting with two of your students, and they were very helpful, like Joe and Rory. And I mean, that helps to get connected the first spot. If it happens, then the ignition has happened and everything goes well. But well, if you don't feel connected at the beginning, then it makes things more difficult as time goes. What I can say is that, well, try to remain open, to remain positive, and it is very difficult to know people remotely, to understand them, but with a little bit of effort, we can do that.
Okay, so if we gave you the opportunity to be physically here, would you prefer that, or it's better your wife is in Belgium anyway? Now that you know how it feels.
Okay, it's being recorded, so I have to be a bit cautious.
And Gert is here too, so you gotta be political about this.
Well, I'm open to both options, let's say.
Yeah. Okay. Well, thank you. I think we have time for one more question, if there is. If not, that's okay. Is there any questions from the attendees? If you do, you can raise your hand. One more question. If not, that's great. Well, thank you very much. I think you did a great job of introducing this. It's quite hard to understand what's going on in these data science areas. I think you did a great job of putting it in a form even I can understand what's going on.
You're smart enough.
And I'll let Charlie wrap up the meeting.
Thank you, Iggy. Naza, thank you again for that excellent presentation and that engaging Q&A. I hope we can have you physically in Princeton at some point. I want to also thank the Andlinger Center staff who are working really hard behind the scenes to support the creation and delivery of this seminar series. And I'd also like to thank everyone for attending today. Next week's webinar will be at 11 a.m. on Thursday, June 25th, where Dr. Lianfeng Zhao will discuss his research advancing the fundamental science and engineering that we need to develop metal halide perovskite solar cells and low energy light sources. You can find a link, you can find a link to the speaker series webpage and registration posted in the chat box. We look forward to seeing you at future talks. And in the meantime, stay safe and healthy and have a great week. Thanks again.